try to be quick, but feel free to depart as your schedule dictates. I may use a few minutes longer.
I do have a question. Do you have office hours tomorrow morning?
I consider the lab as office hours. But if let's exchange emails. I will be on campus at 11 tomorrow.
Okay.
So please start thinking about what will be your project, and do not hesitate to take some very wild ideas. A couple of years ago, it was like lipid bilayer interacting with the semiconductor surface. Today, maybe some of you may want to simulate coronavirus, which could be attract a lot of attention. So we are completed 2 chapters and started the 3rd one. This is the most important chapter, and by the end of this month, there will be one more presentation on VASP software. It is the main tool for the project. I think we will use about 3 weeks. Next week there is a break, right? So probably we do not meet, but I will be happy to exchange emails, and the connection will be active, so we may use this facility to chat online. This chapter will go to show how the density function theory algorithm works, and there will be some similarities with how to talk algorithm. It is why we spend a month on it, but there is a different philosophy, and there are some theorems that prove the background that density functional theory must work. There were a lot of clashes in the community to tell that DFT is not a true theory, it is just a set of rules, but there are strict mathematically proven theorems that which it must be correct answer. Even if you never use these theorems for mathematical derivations, it is an important cornerstone, so that after you fabricate some research results with density functional theory, if your opponents try to say that results are not trustworthy, you can claim that it's maybe problems with implementation, but there are theories that your results are correct. And we will spend some time. And there is an algorithm, there is a flow chart that shows what is getting optimized. There is an analog of molecular orbitals, but it will be a little different philosophical contents. Okay. And in the labs, once they in sessions, we get through practical steps of using software. To write about this time, we will start investing effort into the project. This is like a script of lab that we haven't completed yet, so I'm skipping. It is basically what we will do evening. And in the previous lecture, set of lectures, we were considering how to set Fock operator and how to use density methods, which is square of the expansion coefficient, and basically those elements evaluated at a specific atom provide the European charge. So you may have used this equation for representation of the European charge. This is how we formulated Fock, and last time we were discussing interaction with light, or the main achievement was that transitions from one multi-electron state to another multi-electron state can be expressed in terms of transition between one of the initial and final orbitals that are getting changed. This concept of dipole equation to the Hamiltonian equation for dipole and this transitions will be used again in our new chapter, in our new software, to compute transitions from ground state to a state where the orbital I could flipped orbital G. And the measure of such optical transition is integral of this initial and final orbital with position greater than for the whole space, and this object is called transition dipole. This is the measure of ability of your model to respond to electromagnetic propagation. You will not focus on just bringing it again and again so that you get used to see this equation through the upcoming step. In periodic solids, the specific pattern, like in polymers, is repeating again and again, and we will be using software that is intentionally designed to describe periodic objects, or the wave functions at each replica, at each monomer, will be very similar to each other, but they will be different by exponential phase factor. And we completed previous academic lecture with Koopman theorem, with ionization energy and affinity, that you've got nice questions and discussions from Professor Han Kwan. Right? You remember? Okay. So this is the list of subjects that you need to cover in the labs, and one day we will fill sign up sheet, so you may also start opening and design what you are interested in. It gives you heads up what you cover in the lab. And now we are starting a new subject. So in the previous month, in the previous section, the core C5 task was to work out some approximations for multi-electronic wave function that depends on positions of first, second, third electron, and through this approximation and some algorithms to obtain total energy. If you do not care about such observables like ionization, affinity, band gap, optical transitions, if you are interested only in chemical reactions, the practical goal of this arrow is that we follow what Rebecca has presented. We shift positions of ions. At each position we find total energy. We define if energy increases or decreases or has a minimum and a barrier. Then we can compute how much energy is needed to overcome the barrier and perform chemical reaction. Clear, right? The concept of multi-electronic wave function, the concept of molecular orbitals is good. There is a substantial segment of researchers in the community who love and continue to pursue. And since the course is rather short, I will be very quickly reviewing the add-on theories, so-called post-particle theories that Rebecca is aware and Steven was introducing in the first presentation last time. So there are only two other numbers: perturbation theories that add corrections, make protocol results more precise. There is a so-called configuration and interaction theory that introduces multiple excitations and continuous our path to higher precision. And there is a couple of clusters that uses completely different philosophy. It reduces Schrödinger equation from chemistry into a set of non-linear algebraic equations, but also provides very high precision total energy. But they all are based on the concept of wave function. It looks like we are confined. We can only give more precision in how we deal with molecular orbitals that are entering into the later determinants that give a total energy. But there is we can think out of the box and change the approach to our tasks, to get total energy drastically. So the opposite philosophy is today it looks natural, but originally it was a little crazy. What if we abandon any wave functions and look only on the distribution of charges in space? In our mean field concept for the particle theory, the charges occupy molecular orbitals, create background field, and this background field, this interaction of last electron with all other electrons, this background field, determines properties of the system. Right? If the background field from the charge distribution determines all properties of the system, then philosophically we do not need wave functions. We need only this background field or just charge distribution. It is not clear how to convert this charge distribution into total energy, but the idea is that you stop thinking about wave functions and you start thinking only about charge distribution. And we hope that there is a path, there is an arrow that will bring total energy with all quantum mechanical effects. So this is basic functional theory in happening. Good. So the plan includes several steps. So we need to go over definitions. Like we know what is theory, but we may discuss what is functional and what is density. Just to agree on the subject. Today, most of the time, you saw that there are a lot of slides. I will try to skim quickly. I have send links to YouTube. There is a background theory called Thomas Fermi theory that has no relation to practical computation of molecules and solids. It's completely abstract concept, but it sets up a philosophical cornerstone how to retune our mindset to stop thinking about wave functions and start thinking about density. So if you miss it, if you close your ears and eyes today, you'll miss nothing for your practical computations. It will be only a little philosophical concept. And later on, not today, we'll go through theorems, practical algorithm, and we same as we did at the end of chapter, we will discuss how to convert computations into observables that can be compared with experiments. So, who was presenting charge distributions? Okay. Not Malkin charge, it's like how many electrons are on certain atom. And charge distribution, like density. You did it as well? So there are orbitals and there is a density. Which means if we know the orbital and we have orbital squared, we give a probability to find an electron in a certain position of the space. If we integrate this thing over the whole space,
if you give one because there's one electron on one orbital, right? If we add together the distribution of charge of each occupied orbital, first orbital, second orbital, up to the whole, we will get distribution of all charges that is responsible for a ground orbital. And if we integrate each of them, or all of them together over the whole space, what will be the number?
1.
No. 1 if you integrate first orbital.
Number of
Exactly. Number of electrons, right? We integrate here, we get 1. Integrate here, get 1. Integrate here, get 1. And then it will be as many electrons, occupied orbitals in this system. Since if we do not do unrestricted, if we just do singlets with 2 electrons per orbital, it will be 2 times number of holes under the. Now, it looks like very challenging. No one objects, no one feels comfortable. But there is an important background that we did convert a function, which is distributed function in space, into a single number. So, like same as scalar product or same normalization, but when we start calculus, we define a function as 2 objects of the same size and dimensionality. For each x, we have one. For one x, we have one value. Right? If you plot a function, if you represent function numerically in Excel, you have 2 points. One for argument, another for function. Right? It's 1-to-1 correspondence. For one number, you get another number. For one vector, you get another one. But here, we are converting a function into a number. Right? So not number into a number, but function. It's quite simple algorithm, you just integrate it. But this procedure of converting a function into a number is something different. It should have different name. So instead of function, one call it function now. Okay? And instead of round brackets, one put there is no absolute convention, but most of the people use rectangular brackets to highlight the fact that number of electrons is functional of charge distribution. So the charge distribution is charge density, right? Because in some regions of space it's more dense, in another it's more sparse. Charge density. Now you know what is function now, and we do theory of it. So you have a basic idea what is density function of theory. The only, we will talk about it for a month, but the only difference from this little slide that we need to obtain total energy as a function now of charge distribution. Okay? And it is worth of that. So today we will not answer on how to get total energy of real molecules or solids. We will consider a spherical horse in a vacuum, an abstract object that doesn't exist in nature. It will be abstract theory that has similar philosophy to density function theory. This theory designed by, I don't put the name, Thomas and Fermi in 1927, and it was not used, it was used just, they published a paper and everyone forgot about it. But later on, one found that it is something philosophically important, because it is the first theory that attempts to convert density into energy. So that you do not invest too much of your intellectual efforts, I want to give a little disclaimer what this theory doesn't do. So this theory doesn't have any nucleons. It considers a universe free of ions, free of nucleus. It has only electrons. And these electrons in the universe do not interact with each other. So it's completely irrelevant for practical calculations. But it has more than one electrons, multiple electrons, and if one starts to analyze this model, a lot of logical steps, a lot of approaches can be borrowed and later used for the density function theory. So after the disclaimer, you decide yourself whether you want to focus on the material on the lecture or just use the time for relaxation. There is a panel on the left that shows a plan, logical steps that I will try to go over, and at the end of this 8 steps, it will be more than 8 slides, but logical, there are like 8 steps. At the end, we will have the total energy as function of the density, which we will define. And the protocol, the connection between density and energy, will prompt how to act in the future for more realistic situations. Divide and conquer. Told mentioned before this. Even for this auxiliary space, auxiliary universe, with a lot of non-interacting electrons, it's too much to be considered at once. We may want to chop the space on the smaller boxes, smaller elements. And then by chopping it on the elements and then recombining back, one can get important consequences. Why we are chopping? What is the size of the boxes? At the time when this theory was introduced, there were not many quantum problems that can be solved analytically. And there are not many now. And one of the problems that can be solved is particle in the box. Okay? So if we confine an electron in a box, the set of quantum states, of like orbitals, and their energies and shapes are known for sure. It can be solved. So we chop the universe on boxes because the solution for a box is known. And the one-dimensional box, two-dimensional pizza box, or three-dimensional USPS boxes are very much solvable. So if you tell that your electron is in the USPS box with hard walls, one can find solution immediately without any computation. So if we follow this idea, we may want to quantify the size of the box. Let it be letter L and let it be Q. Then volume of one box will be LQ. If we do chop total number of electrons in the universe and over these boxes, then in one box there will be delta. And then in one box there will be delta n electrons per volume LQ. Okay? So this will be density. In this universe we will assume that electrons are homogeneously spread like butter on the bread or the whole universe. So the density will not change as we go from box to box. So it's quite sealed.
Yes. So all the electrons are assumed to be distributed uniformly?
Yes. But I know how silly it is, but it will give very helpful mathematical concept. And if we set up the density and we can find energy in one box, then later we will add together energy of all boxes and get the total energy. Right? Why we are doing this? What is the benefit of this sealed theory? In this protocol, one would omit as much as possible any mentioning about wave function. Although we know that they exist, we will try to exclude wave functions completely and formulate energy only as functional of density. Once again, why density is needed? Because it is so much, it includes information about all electrons, but instead of Slater determinant and product of many wave functions that equations in space, this is very compact object, right? Multi-electron wave function, we were making assessment how many terabytes, petabytes I need for like a small molecule if everything is done literally. If one accepts that all information about properties of molecule is stored in the density, one will need only like, couple thousand or 100,000 grid points for any system. So it will be the amount of information needed to store the information to run this algorithm will be growing much slower, will scale more beneficially than any wave function field. This is a reason to invest effort into this oversimplified theories. Okay, 15 minutes until noon, and the majority of slides are I didn't start them yet. But at least we agree on the background. The rest of it. So let's focus on a single box. If we have one-dimensional box, this is an equation that most of us enjoyed in physical chemistry or basic quantum theory. So the analogs of molecular orbitals, eigenstates of electron in one-dimensional box, will be sign functions, and their energies will grow as square of the quantum number. Right? Number of the eigenstrates. So as number grows, they become more and more sparse. And the energy depends, it originates from kinetic energy. It has constant mass at front, and it also includes the size of the box. So if the box is large, the quantized energies offset from each other insignificant. If you take very small boxes, the offset between energies will be noticeable. Right? Quantum confinement. If one goes from one-dimensional box to three-dimensional box, the equation for energies will have the same nature, but instead of one quantum number, there will be three quantum numbers. So energy depends on three quantum numbers on x, y, and z. And there will be still square of the size of the box in the denominator, and squares of these quantum numbers will be in the denominator. You don't want to agree with this. what do you think when you're looking at this equation? First thought, okay, it is 10 minutes before my lunch, I will be partners. What are other thoughts you may develop looking? Does it look similar to anything you have seen in your career, especially your career at middle school and high school? Yes, super, excellent, yes. It looks like distance from the origin. So you can call the energy to some sense, it is distance from the origin in the space of quantum numbers, right? Or distance squared. So we will be browsing in a three-dimensional space of quantum numbers for each box. Very good. I'm happy. So distance is x squared, y squared, z squared, right? Squared. And now we can. So what is the goal? Where we're going? There, we do need to perform the same thing as we did in Hartree-Fock with filling electrons on the molecular orbitals. Our Bohr principle. We need to count all available states and put electrons there, right? And in order to count all states, we need to design something more comfortable than this radius equation. We need to maybe make inverse connection, like how, if I know the energy, what will be the index, or get more, what is the degeneracy at certain energy. So we need just more information about structure, electronic structure, maybe density of states of this particle in the box. Right? Like how dense are states. We know intuitively when quantum numbers are small, there are offsets and it will be sparse. As soon as energy increases, there will be more and more states where, like, quantum numbers, for example, like 3, 1, 1, 1, 3, 1, 1, 1, 3. It's different quantum numbers, but energy will be the same, right? And when we go to higher energy, such instances of degeneracy will repeat again and again. And we need to quantify this degeneracy. So what if we look on the question how many states are between two energies, or between energies that are offset from each other by a little change in this distance. So we are browsing in a space of quantum numbers, which is three-dimensional. We know that energy is just distance from the center. So if the distance from the center is fixed, energy will be the same. And now we need to look on a very thin layer, the surface of the sphere, and count how many states are on the surface of the sphere, which will be degenerate. This is an example of the same situation in two-dimensional space. Because I am a bad drawer, I would fail to do it three-dimensional. So if you have quantum number on X, quantum number on Y, the points are pairs of quantum numbers, eigenstates of particle universe, right? So state 1, 1, state 2, 1, state 1, 2. And if we go to the quite high radius, and we look on the stripe, there will be multiple states that do have the same energy. Right? Can we count how many states is in this stripe? I'm sure each of us can. At least we can count. At least we can count. Total number of points, total number of states inside of this quadrant, which will be, how do I count the area of a circle inside the circle? Huh? Area of a circle?
Area of the circle. What's density of the electrons?
Yes, but if it is just arbitrary abstract space, two-dimensional area of a circle, yes, right? And if it is quadrant instead of the whole circle, like segment, it will be a quarter, 1/4 of PR square, right? If it will be octant of a sphere, and we look on the volume, what's the volume of a sphere?
Over 2 pi r square.
R cubed.
Oh.
Yes. Yes. And if we look for octant, like 1/8, if all arguments are positive, then it will be 1/8 in front of this, right? Okay, so we do have amount of states inside this sphere. And now if we need only thin stripe, we can just make derivative, right? If the thickness of the stripe is infinitesimal, we just make the derivative of volume in respect to radius will give the surface, right? So derivative of the third power will be second power. We're not going to argue this now. Okay. And 3 goes into up front and probably cancels with this. So we do know how the amount of states, how the degeneracy depends on the radius. And if we need the actual number, we need to multiply by the thickness of the stripe. So let's try to follow this 3 equations. Number of states inside of a sphere of a given radius can be expressed by this volume equation. But we do not, this radius is too much abstract. Can we, instead of radius, use the energy, which is just radius squared, right? So can we substitute and replace r with e? So this distance, this abstract radius, is square root of energy and then square root of all these constants, which includes the size of the box. And if you plug in this, definition of radius into here, we get energy, square root of energy into the third power, which will be energy 3/2. Very interesting. Number of states that does have the energy epsilon equals some constants times energy to the 3/2. Number of states that have certain energy. Who was presenting density of states? Do you see connection? So number of states with certain energy. So for this universe with non-interacting electrons, we do have density of states without any computer code. Right? So it just grows with certain power. And in some sense, we may want to find density of states of any atomistic model, right? With two ions in the future. In simple models, we know what it is. But our goal is to get energy as function of density. So let's keep going further. So this is density of states, which grows as function of energy. What would we get if we take derivative I did lie a little bit. E to the e to the power of 3 halves is number of states, and derivative will be density of states. Cool. So we need to take derivative, and then it will be number of states per energy interval. Now, the next step, we do need to mimic the Aufbau principle. So, by analogy with any molecular system with hydrogen atom, we do have sets of states. But we know that there is a certain amount of electrons, delta n per box, and we need to distribute this electrons. How many orbitals will be occupied by n electrons? Delta n orbitals will be occupied. But if we want to exclude the number of electrons and replace it with the energy, can we, instead of telling what is the number of HOMO, can we tell just what is the energy of HOMO, up to which energy orbitals will be occupied? So this question is related to the Fermi statistics that comes from statistical mechanics. I did send you a link to YouTube. It's not a big secret. So the equation is here, and it tells that there is a critical energy. Below this energy, all orbitals are occupied. Above this energy, all orbitals are unoccupied if temperature is 0. If temperature is above 0, then there is a promotion of orbitals close to Fermi energy from occupied to unoccupied energy. And if you try to plot this energy, which is occupation of orbital of energy epsilon, as function of energy and temperature.
It's a logistic regression.
Huh?
It's a logistic regression.
Larger what?
Logistic regression. It's a model that the result should be 0 or more.
There should be 0 or 1 if we set T equals 0. If T is room temperature or like high temperature, it will be continuous change of occupation. So if you try to plot, exponential is growing, 1 plus exponential also growing, and then you divide 1 over this function, which is at minus infinity, it is 1. So 1 divided by 1 will be 1. And energy equals Fermi energy, it is denominator is about 2, and 1 over denominator will be 1 half. And then this denominator goes to the infinity, and 1 divided by infinity will be 0. So just mechanics how Fermi distribution works. But if temperature equals 0, then this becomes a step function. Sharp 1 before Fermi energy, sharp 0 up. So we do want to merge together our concept of density of states and the fact that only states below Fermi energy are occupied. Right? It's something that we can do. But now we do need to make the following logical step. A little trick. we need to convert number of electrons in our box into Fermi energy. So we need to connect them. Who was taking or practicing statistics? Good, excellent. What do you think when you hear the word moments? Not momentum, like in mechanics, but moments. No? So, no, not like pleasant moments of life, but moments in statisticals, in sense of statistics, or in sense of distributions. Like, why distributions are needed? How one utilizes it? If you have, for example, consider we all are assigned to teach a big freshman undergraduate class with 300 participants. And we give a quiz with number of points ranging from 0 to 100. And then we have number of students that got like 50 points, 51 points, so and there is a bit of a distribution.
A lot of distribution that gives us a median,
exactly.
Average, or
so,
something like
yes. So if you take this distribution, multiply it by the variable corresponding to the grade, and integrate, it will be expectation value of median grade. Right. So generally, it's called moments of the first order, of the second order, and then yeah. So the same philosophy is here. So if we need to find the energy of the system, we multiply the energy times distribution and integrate it. So we take two components. We took density of state and we take occupation, because not each of the available states are occupied. And if you perform this integration, it will mean that we just add together energy of all occupied states multiplied by degeneracy. If there is more than one state, we add this energy together more than once, right? But in more generally, in sense of statistical distributions, it's like one of the first order moments. How do we do it? We omit this occupation. Instead of doing, because occupation is either 1 or 0. So until energy equals Fermi energy, it will be 1. After that, it will be 0. So we just limit our integration from 0 energy to Fermi energy. And then we multiply it by degeneracy, or by density of states. How many states of certain energy. But we do know this density of states is just square root of energy, some constant. So E times E1/2 will be E3/2. What happens to the power after integration? Increases by 1. So after integration, it will be 5/2, and the let's keep constant. And we evaluate this integral from 0 to Fermi energy. 0 e to the power 5/2 will be 0. So we have only Fermi energy into certain power, 5/2. What did we get? We got the energy of all electrons in the box.
Fermi energy was 1, right?
Huh? No. Fermi energy is energy of HOMO. is the energy of last occupied state in the system.
But you normalize it between 0 and 1. The upper
I
limit.
wait. There is Fermi energy and there is Fermi distribution. I'm going to switch one slide back. So this f of E is Fermi distribution, and this value, Fermi energy, is a parameter, is a number. But the total energy of the box, which we finally need for our goal, is just Fermi energy into a certain power. Right? And opposite, we can formulate Fermi energy as a certain power of total energy for this system. We do need to formulate everything in terms of density, number of electrons per volume. We know the volume, we cannot pick it. But can we express number of electrons in terms of Fermi energy to have everything consistent? Yes, we can, and we just remove epsilon from this integration. So we integrate the density of states in the limits from 0 to Fermi energy. So we integrate all occupied states. Because this is degeneracy, so we just add together how many orbitals we have. And at certain averages, some of them are degenerate. Right? So if this degeneracy, if this density of states is e to the square root of energy, right? Upon integration, of 1/2, we get 3/2. Okay? And some constants. I just do not work them out because it's not a main message. And then we evaluate this e to the power 2/2 from 0 to Fermi energy. Now, number of electrons in the box is Fermi energy in the power 3/2. Catch me if you can. Nothing is wrong, right? Straight logic. So everything can be expressed in terms of Fermi energy. Or we can swap the direction and express Fermi energy as function of number of electrons, right? So by now we have total energy of a box is Fermi energy 5/2. Number of electrons is Fermi energy 3/2. So if we invert the dependence, then Fermi energy will be number of electrons in the power 2/3. Right? But at this point, we can use the Fermi energy, which was expressed in terms of number of electrons, as an input for the equation of total energy. Right? So we are going to plug in this number into this equation. And then total energy of a box will be number of electrons per box in the power 2/3 in the power 5/2. So we can cancel this 2 here. So number of electrons in the power 5/3 will give the total energy of a box. We are very close. We are almost done. Here we express total energy of a box as function of as number of electrons in the box, and we need a density. So we can do a little trick and divide and multiply this number by the volume and call it density. So if we divide and multiply by this L to the third, we need to refer this L to the certain power into the constant. We did so many approximations of leaving the process of constant for the future. We can put stuff there and work it out if we need it. But then here we do have number of electrons in the box per volume of the box into the power for 5 cells. And the definition of constant is different. You can put many things, but energy of a box is density of electrons in the box in the power of 5 cells. Right? I didn't like it. After this, we may want to take energy of one box and then integrate over a 3-dimensional space because there are so many boxes. Right? And all constants which we were postponing can be expressed working out of fundamental constants and call it like Fermi constant. But the idea is that total energy is a functional of a density. And functional is density into power of 5/3 integrated over a 3-dimensional space. We didn't get a step forward to describe any of the practical problems. But philosophically, we do see that under this tweaking our mindset, there is a way to express main observable total energy just by processing density of electrons. No wave functions. Density determines total energy. Of course, this theory is very imperfect. It doesn't have ions. Electrons don't interact with each other, but it has main component connection from density to total energy. This connection of density and total energy will be used. It is the standard thing of the density function theory. In the more advanced implementations, when we get to the true practical density function theory, in addition to density, there will be more arguments for this function. For example, gradient, the derivative of density in respect to space, and some additional connection. But the function of a density like this simple integral is the main part of the density function theory when we get to its implementation. We will take a break from practical steps and consider some theorems for 2 lectures. But later on we will return to this connection between density and total energy. Many thanks for your patience. I look forward to seeing you on Wednesday evening in the lab. See you.
I have any question.
Yes,